Hi, my name is Thomas Bhattacharya, and I would like to give a quick presentation on reasoning models, specifically the applications and the business benefits that can be accrued from these. Let me begin. First, let me clarify the objective and the target audience. This presentation will get into what reasoning models are and how they enhance the typical LLMs that we all know. We will go through the defining characteristics of reasoning models, and we will aim towards a roughly intermediate level of technicality so that business side stakeholders can have a thorough understanding of what these reasoning models are and what they can and cannot be relied upon towards. So that we will not be going through the actual implementation or engineering decisions that may not be relevant to the target audience, but rather we will try to make sure that business side stakeholders have a clear understanding of how these reasoning models can address specific business applications in a manner that is more nuanced. And finally, we will go through a set of business applications to clarify these so that we can see exactly what benefits we can get from these reasoning models. Let me begin. So what exactly are LLMs first, or what we call AI to begin with? What we have AI are basically foundation models that have been trained on extremely huge amounts of data. They have been trained to generate natural language, and they can seem to conduct conversations with users, which is actually what they do. And they are extremely sophisticated examples of natural language programming applications. They are, however, generalists. What they really do is that they create content out of patterns that they have been trained upon. And these patterns can become very sophisticated. They can use multimedia contents for models that are first trained. And recently, these models have completely burst into public consciousness with the term AI. But it is perhaps very helpful to bear in mind that they are simply a culmination of years of advancements in natural language understanding, natural language processing, machine learning, and deep learning. Although what has been combined for these have been the sort of resource dedication that have been rarely, if ever, used for these purposes. Now, let's look at the basic technologies that allow LLMs to operate. LLMs will yield in foundation models. This term is thrown around a lot. Now, what are they exactly? Now, let's go back to our more usual machine learning or deep learning models. So what happens is, based on data that has been curated properly, a model is trained, perhaps using PyTorch or other similar frameworks. These models are then deployed and they ingest the data and spit out a particular understanding of the data or particular decision making based on that data, which is to say they're quite specific. They have been exactly tailored to solve one particular problem. Foundation models are, however, an extremely large and extremely general NLP application. So that what they really shine is that a single model can be used to do many different things rather than one clear-cut use case. The second thing we need to look at is the transformer model, a transformer architecture rather. A neural network architecture which is based on the multi-head attention mechanism. This is as opposed to what used to be used called recurrent neural networks or RNNs. The multi-head attention mechanism tends to consider an entire set of words together. It tries to look at the interplay of words to gain an actual context into what the words mean together. RNNs, on the other hand, tended to consider sentences word after word. That is where the basic difference lies. And the net effect is that this model will gain a greater degree of understanding of the context of the text that is analyzing. And this allows for seemingly greater language understanding and logical inference on the part of the model using transformer architecture. Now, reasoning models, what are they exactly? Reasoning models are LLMs that employ certain techniques to end up having an operation pattern that will decompose large tasks into smaller tasks and solve them one by one in a logical step-by-step fashion. That is, and which is where the reasoning nomenclature comes in. It seems to reason in a logical step-by-step manner. Clearly, the aforementioned techniques, they're often related to the way the foundation models are prompted. And it is this prompting that yields the step-by-step reasoning behavior. These smaller components of reasoning models are often referred to as being reasoning traces. The actual output of the model for any query then ends up incorporating all of the accumulated processes over all of the reasoning traces that were generated in response to the query. This contrasts from a direct response pattern of most foundation models, where they will simply take a query and end up spitting out a result. Nothing in between. No matter how complex the query is, it'll give one direct answer. Reasoning models are useful, very useful, because they can be used for very sophisticated and rigorous logic-driven tasks, like generating programming codes, solving mathematical problems, etc. And they have been benchmarked to provide performance gains over previously employed mechanisms. This is where reasoning models come to show their effectivity. Also, these benefits accrue from the model's behavior of undertaking multi-step decision making, which can be used to actually explicitly spit out the chain of thought tracing of the model's operation, which even a casual observer can readily take note of. Many specific techniques are used to bring this about, usually prompting techniques. So, what is the use of this? Why do we care? We care about this because it seems to break the black box. It brings about a certain degree of transparency to the way a model is operating. So, what it does is that it will decompose any query that it is operating on, and it will emit a step-by-step description of the logic that the model itself is using. And this particular chain of thought can then be observed so that the actual operation of the model is understood. This particular operation style can be called a chain of thought, where every single operation is observed down to its basic building blocks. And even a casual observer can gain an understanding of the lines of reasoning that the model has undertaken in generating an output. And this gives the basic primary benefit we get from reasoning models, that of observability. And from observability, we get explainability. We can explain why a certain decision has been reached. And because we can do that, we can also audit these processes. So we get observability, from which we get explainability, from which we get auditability. And now we can actually sort of give a defining characteristic to a certain decision that has been reached by the reasoning model, rather than just getting something out of the black box. Now let's discuss this transparency a little bit more. A 2024 Google DeepMind paper claimed that any increase in test time compute, that is, any additional resources supporting the model's output generation, results in increases in the model's performance that is comparable to the effects on the model's performance due to resources used in the initial training. So when we use the term test time compute, we are referring more towards something that's been done after the pre-training. And this paper argued that such engineering can have effectivity that is comparable to the pre-training of the model itself. And that is exactly what we see in reasoning models, which are prompted to derive a chain of thought style behavior to further refine the effectivity of the model's output. There are various other techniques that are also being used. Primarily, one can note reinforcement learnings, which can be used in this case because reinforcement learnings, as opposed to, say, self-supervised learning, are better suited towards open-ended behavior. The way reinforcement learning roughly operates is by giving rewards to a certain kind of behavior exhibited by the model that is considered desirable. So that is a way of making sure that the model is behaving in a manner that is preferred, that is helpful, rather than explicitly putting that into the training beforehand. And this is very well suited towards open-ended operations that we see in LLMs. One common explicit pattern is known as the reinforcement learning for human feedback, which is used to shape the initial output of the model in a manner that is more helpful based on human preferences. Now, let us go into explicit business cases. In the finance or banking domains, it is often seen that legal regulations can require that negative decisions upon topics like, say, providing loans be explained, which is there with the objective of making sure that there are no biases and discriminations built into this decision-making process. Now, if we had an LLM which simply emitted a decision saying yes or no, there would be no way of verifying that these concerns are taken care of into the reasoning model's operation. So that is why the reasoning model will articulate its chain of thoughts. It will spell out clearly what decision factors were taken to either result into a positive or negative decision, so that the validity of this decision can be objectively checked by a regular observer. Aside from this case, it is also a known thing that the sheer volume of financial transactions necessitate the use of fraud detection models in financial crime fighting. Now, typically, a model would simply flag a particular transaction as being potentially fraudulent or not. But what reasoning models can do is that they can enumerate the factors that led up to the model emitting that particular decision, that particular flagging of a transaction as being fraudulent or not. Not only does this help with observability and auditing, it will actually also help human agents, human security professionals, in going through the incidents that have been reported and trying to understand the patterns in them in an easier manner. In medicine and pharma, reasoning models can be relied on to give advice to doctors regarding the diagnosis of symptoms and the proposing course of treatments. In these cases, we have to elucidate the factors given by the models so that the validity of these can be checked by the doctors, because it must be noted that while the value added by the models in assisting medical professionals comes from relying upon a vast corpus of medical literature that the model has been trained upon, it still holds that the decision making must be taken by the doctors. And to do that, the doctors have to know what kind of decision making process was actually followed so that the model gave the ultimate decision and the advice that it gave. In legal use cases, as we have seen, reasoning models can also mine vast tomes of legal documents to refine a set of documents or a set of factors from the underlying documents that may be pertinent to a particular legal inquiry. In such cases, the legal professionals would benefit from being aware of the factors supporting the choices made by the model. This can form a sanity check on the ground, and it can also explicitly spit out case details alongside legal documents or evidences, which can help refine the structure of the materials that the legal professionals are working upon. Similarly, in cases such as insurance claims processing, we can also use this similar pattern of decision-making transparency to make sure that the model is behaving in a manner that we can consider to be acceptable and valid. So, in final note, what exactly are we doing here? The net effect of reasoning models is to yield AI models that can operate upon humongous textual data and provide insight based on patterns in them, but along with an additional property of articulating the factors behind the decision-making models. This allows for the analysis of situations provided to the users of the systems. This breakdown of analysis allows for transparency, the ability to validate the processes undertaken, and thus to have confidence in the process. Thank you so much. Thank you so much for your time.